Hello, and welcome to a review of HPC technologies in Ansys HFSS. My name is Matt Commons, and I'm the Principal Product Manager for the high-frequency products at Ansys. And I'll begin today's presentation by posing a question. What if you could solve these? What if you could solve complex models like this DIMM module with PCB plus 8 packages, all while preserving complete 3D electromagnetics, or a 256-element 5G millimeter wave antenna array, or a PCB plus connector plus DIMM, again, with complete 3D electromagnetics with HFSS. Or imagine you want to solve full physics models of a W-band automotive radar, including a range Doppler output, and possibly even in real time at 30 frames per second. Well, this is all possible with HFSS and Ansys HPC technologies. Now, this presentation is going to be focusing on HFSS, and with HFSS, let's remember the one real value of HFSS, which is the accuracy and reliability that comes to us from automatic adaptive meshing. Here we're seeing an example of a 4-element patch antenna with its mesh being adaptive and its return loss stabilizing to its final value. Automatic adaptive meshing gives us an efficient solution by only placing mesh elements where needed, an accurate solution by having those elements placed according to Maxwell's equations, and ultimately delivering reliable results so you can make design decisions with confidence using HFSS. Now, from the earliest days of HFSS, there's been a need for speed and capacity, going back to 1990 with the first simulation of HFSS of this coax to waveguide transition. Size of the problem was very modest, very small, only 10,000 in matrix size, but with hardware of that day and age, took over 10 hours to solve. But even in that time, this was revolutionary. A 3D full wave solution of a device like this, where you could visualize fields and extract S-Parameters, was absolutely unheard of. But from this point forward, simulation requirements have just scaled up. They've scaled up in size as well as in complexity, and sometimes both. But as hardware has evolved over the years, HFSS HPC technology has evolved right along with it. And one of the first HPC technologies to talk about with HFSS for faster simulations is matrix multiprocessing. Matrix multiprocessing was first introduced back in the late 90s when multiprocessor desktop computers became more and more available. And with multiprocessing, or MP, HFSS users could simulate faster and get products to market faster. Now, the latest technology leveraging MP basically takes advantage of multiple cores to solve the dense frontal matrices along the sparse HFSS matrix. You can picture it as something like this here, multiple cores, each one assigned to a particular dense frontal matrix, solving those frontal matrices in parallel. Now, the earliest technology could realize anywhere from 2.5 to 3.5 speed up, depending on problem size and cores or hardware, but it was somewhat limited. But with modern hardware and modern multiprocessing technology from Ansys, as applied to a more complex design like this DIMM connector that was recently highlighted in the Ansys white paper, we can solve these models fairly quickly and fairly conveniently with the MP technology. This model size, 2.3 million tetrahedra, 10 million matrix size, so 3 orders of magnitude bigger than the coax to waveguide transition, and leveraging our hierarchical mixed order basis function. We realize over a 5x speed up using up to 10 CPU cores for the matrix solution process. In addition to using multiple cores, you can also leverage a GPU for the HFSS finite element frequency domain solver. What the GPU does is it works in combination with CPUs to provide overall about a 2x faster solution, again, depending on problem type, problem size, problem complexity. And conceptually, the way this works is, again, we look at our same sparse matrix, FEM matrix from HFSS. We have a number of dense frontal matrices that have to be solved. What we do with the GPU is we apply it to the largest, most difficult dense frontal matrices, since GPUs can tackle those very, very efficiently. And that gives us this extra 2x speed up on top of the speed up we get from multiple CPUs. Now, we can go larger. We're not limited to memory on a single computer to use HFSS and solve in multiple processors. There's a technology called distributed memory matrix solving that allows us to use the same matrix solver from HFSS and not be limited to one machine. And the virtue of this technology, this distributed memory matrix solver, is we can now access more memory and more cores on network machines. But we're still using the very accurate direct matrix solution technology, which provides us the lowest noise floor and best efficiency, especially for designs with many ports. But in the end, we're still solving a fully coupled electromagnetic matrix, and so we're not compromising the accuracy of the solution. Now, conceptually, it's pretty simple to understand. Here, what we're doing is we're applying these multiple machines to solve those dense frontal matrices in parallel to speed up the overall solution process. And in the first introduction of this technology back in 2014, we applied it to what was then a pretty big model, this trunk-mounted antenna, tens of wavelengths in size, matrix size of 12 million. We were able to address over 0.5 terabyte of memory and really open the bounds, open the possibilities of what you could solve with HFSS in a very, very reasonable time, in this case, 3 hours. And capability and technology has grown from there. We can now solve models like this 8-layer DIMM module, which will be reviewed later on today in a presentation by Dennis Soldo. Take a look at this design. 8-layer PCBs, 2-layer packages, 8 packages in total of 128 ports across 64 signal lines, solved using the Ansys cloud, which we'll talk about later on, in 7 hours. That's really remarkable. 21 million matrix size, 128 ports, very, very complex PCB plus package design, in only 7 hours. And look at the max RAM requirement, only 32.75 gigabytes. That's amazing, but that's one of the values, one of the real powers of this distributed memory matrix solving, allowing us to apply a modest set of memory on a single machine to solve this problem. To look at this in more detail, here's that same simulation. We're looking at the S-Parameter results. Notice we get very, very low noise floor solutions from that, which can be important, for example, when you have designs with very tight skew margins. But take a look at the profile. Here, in total, we're using 262 gigabytes to solve the problem, but they're distributed across 8 machines or 8 distributed processors. So again, the max memory requirement, the max requirement for a single machine to solve this model would only be 32.75 gigabytes. And of course, if you added more machines, your max memory requirement would go down. So DMM is a really, really powerful technology that opens up boundaries for what you can solve with HFSS. Now, we can also apply this distributed memory matrix solving to what I'll call extreme complexity, solving HFSS on chip. And later today, Brian Boots will be presenting on new HFSS simulation technologies for complex designs from hours to days. And he'll be doing a historical review of some of the HFSS technologies, and I won't go in detail on it, but ultimately, in the end, what will come out of this presentation is the realization is that you can solve very large and very complex sections of an RC IC, solving up to over 100 million matrix unknowns. That's really amazing. 100 million matrix unknowns is a phenomenally large simulation, and it can be achieved with the distributed memory matrix solver. Now, another technology we can apply for faster HFSS simulations is what I'll call HPC frequency sweeps. And once we have the mesh created using the adaptive meshing process, we can leverage a technology called Spectral Decomposition Method. And this is very, very simple. Once that mesh is created, we can now solve the points for the frequency sweep in parallel. And as the algorithms have improved over the year, and here's an example of improvements from 2013 to 2014, we went from 25 hours down to 15 hours using 32 cores of HPC. As those algorithms improve, we get speed ups, but also with additional hardware, we can get that day-long simulation time down to something that can be solved in a morning or an afternoon. So this takes us from a validation flow with simulation to a multi-simulation per day design flow. Now we can iterate on our design multiple times in an engineering day and really leverage simulation for design. There's another advanced sweep technology that's very, very powerful and very valuable for HFSS. We call it S-Parameter only matrix solve. And this is a solution technology that comes to us because we're leveraging the trans-finite element method highlighted in the previous presentation on HFSS technology. And this technique gives us a smaller memory footprint overall for frequency sweeps when we're not saving fields. In addition, it gives us a slight speed up in overall solution time. But the memory savings can be tremendous, up to 3x or even more, again, depending on the product. Connector module, we realized a 3x savings in memory from 100 gigabytes down to 31 gigabytes for a single frequency point. What does that mean with that memory savings? Well, when we solve frequency points in parallel on a given set of hardware, we can pack more points in parallel and then overall get a faster frequency sweep. Now, this technology does not compromise the accuracy. You get the exact same identical results whether you're using S-Parameter only matrix solve or not. So here in this example of this 5G substrate integrated waveguide array, you see that the S-parameter values are identical down to the 5th decimal place. So the accuracy is maintained. There's no compromise to the solution with this technology, but the payoff in simulation time is big. In this example of this package on PCB design simulated from DC to 20 gigahertz, with and without S-parameter only matrix solve, we can achieve up to 114% faster frequency sweep, or in other words, a 2x speed up just with this single S-parameter only matrix solve technology. Came out about 4 or 5 years ago in HFSS. Now, we've talked about speeding up using multiprocessing, using distributed memory matrix solving, using spectral decomposition method, using S-parameter only matrix solve. That speeds up our simulations. But what if we want to scale up? Well, we already talked about one technology that allows us to scale up, the distributed memory matrix solving, but there's a second technology called the Domain Decomposition Method. And this was first introduced about 10 years ago in HFSS, and the concept is very simple. You take a given mesh of a design, and you break that mesh up into a series of domains. And this is all automated in HFSS. And each one of those mesh domains can be solved in parallel on network computers. And once those solutions are created, they become a preconditioner for the iterative solution process of the domain decomposition method. This really increases the capacity, just like DMM does increase capacity for providing access to more cores and nodes. And again, the automatic generation of the mesh domains is handled by HFSS. But one of the key things of this domain decomposition method is still solving a fully coupled electromagnetic matrix. The coupling between the different domains is achieved via the Robbins transmission condition. No compromise to solution. This is not a behind-the-scenes divide and conquer or cascading S-parameter approximation approach like other domain decomposition methods. This is a true, fully electromagnetically coupled technique. And to show you this, here's a comparison of DDM versus the direct matrix solver on this antenna on this aircraft platform. You see the far fields in the cut plane lie right on top of each other, whether we're using DDM or the direct matrix solver. Same for the return loss of the S-parameter. So again, no compromise, fully coupled 3D field solutions. Now, how is this achieved? Well, it's achieved again using that Robbins transmission condition to couple between the finite element domains of that solution. But one of the interesting advancements in DDM has been hybridization, to allow us to couple not only between multiple FEM domains, but even couple in method of moments or 3D integral equation domains. This is a really, really powerful technique. This allows us to use different technologies, different techniques, depending on where they can be applied best. FEM, when you have very fine geometric detail, dielectric moments when you have large conducting structures. We can combine them together in one system matrix and deliver an accurate solution. Again, fully coupled accurate solution. And if you watch the evolution of this technology in HFSS starting in 2008, you see that by the time we got the full hybridization for a fully coupled FEM method of moments, we realized, roughly speaking, about a 25x speed up in simulation time and a 25x reduction in memory. So really, really remarkable technology with DDM fully hybridized and fully coupled. Now, DDM wasn't complete. Its next accomplishment was finite-sized antenna arrays. And here what we do is we realize with an antenna array structure, we have a number of unit cells that have the exact same geometry. So we just define one of those unit cells, the array lattice and the array size, and we just start solving the cells, just the one meshing and solving the one unit cell. And then we virtually repeat the mesh and solve for the fully coupled antenna array with DDM. Now, this provides us a full set of unique S-parameters and coupling parameters for all the different antenna elements and all their couplings to the other elements, and provides us full field post-processing, allowing us to, for example, do 3D field visualization or far fields of the entire array. Again, same theme, no compromise to the accuracy. Well, more recently, this finite array technique has leveraged our 3D component technology to further advance this technique. Now we're no longer limited to using just one unit cell. We can have multiple unit cells and tackle a problem like this, where we have a 256 element millimeter wave antenna array with 4 separate 8x8 subarrays, and including impacts from finite sized ground planes and surrounding radomes. This is a really powerful solution. Again, the concept is the same. Each one of these cells is individually solved and meshed, virtually repeated, and then use DDM to solve the entire structure in complete rigor and accuracy. HPC on the Ansys cloud, solved in approximately 2 hours. This is a design that would take a day or more with more traditional solver technologies. So again, no compromise to the solution, but huge scale up in size and speed with HFSS. Now, in other areas of HPC technology, we can talk about parametrics, hierarchy, and then the Ansys cloud. Now, parametrics is the ability to solve design points in parallel, like this example here where we're doing an EMI study of this laptop. One of these rotation angles is an independent design point. There's no reason to solve them in series. They can be solved in parallel. So parallel design points is a way to distribute these design variations across multiple cores and compute nodes. One of the ways of doing something with HFSS is adaptive meshing is guaranteed to provide you an accurate solution for each and every one of those variations. So you don't have to doubt the solution. You don't have to remesh for each variation manually. You're going to automatically get a good solution for each variation. Overall, that increases simulation throughput, and this technology is pretty close to linear scaling and speed up because each one of these design points is independent. So very powerful technology allowing you to do many design variations very quickly on multiple compute nodes. Now more builds from here. Now we can build hierarchy into our analysis. Take this example here, use the Domain Decomposition Method to solve this very large simulation of a helicopter launching from a ship. Each one of these time steps, again, can be solved independently. The size of this problem requires about 32 cores of HPC with DDM to solve one given frame. So we can solve those frames, again, one at a time, 32 cores each. 8 variations takes about 15 hours back when this technology was first introduced. And notice we're solving parameters, in this case in series, and then DDM within each one of those parameter variations. Well, there's no reason we can't solve those parameters in parallel. So we can run, now we can quadruple the number of cores, go to 128 cores, do 2-level hierarchical HPC, where we have a level defined for the parameters, 4 parameters at a time, and then another level defined for DDM, 32 cores DDM for each variation. And we do indeed realize about a 4x over speed up in solution, because again, this parameter variation is pretty close to linear in its speed up. More recently, in 2019, HFSS was deployed to the Ansys cloud, which is hosted by Microsoft Azure. And this provides ready access to high-performance computing hardware and can actually be launched directly from within the same desktop that you're familiar with HFSS. Now, key technology enablers for getting HFSS up to the Ansys cloud were the DMM and SDM technology I talked about earlier. The ability to run and solve across multiple machines, solve very, very large problems. And this example I mentioned earlier, this PCB connector DIMM module was solved in the Ansys cloud with a fully coupled EM solution. So this really allows you to solve at a scale and a speed never before considered. And again, this example will be talked about later today in one of our follow-up presentations. And speaking of those follow-up presentations, over the next 2 days, we'll be talking about simulations for IC package and PCB. Dennis Saldo and Brian Boots will present today following my presentations. And then on June 11th, we'll have a follow-up with simulations for antenna, RF, and wireless. And there'll be some discussions on phased array analysis, design innovation for 5G antennas, and then also some autonomous vehicle radar solutions. And finally, wrapping up with a discussion on EMI, EMC workflows with HFSS. Now, before I conclude, I want to talk about a few more advanced technologies with HFSS, starting with broadband adaptive meshing. Now, certain designs, depending on what frequency you're setting at, you're going to get a very, very different adaptive mesh. A very classic example is a diplexer like this here, where one region of the diplexer operates in one frequency band versus another region of the diplexer. And if we did just a single frequency mesh adapt, we're going to get the wrong mesh in certain regions of the design. But with broadband adaptive meshing, we can use multiple frequencies in parallel to do the adaptive mesh. And one of the nice virtues of this technology is it gets rid of mesh frequency uncertainty. We can remove that uncertainty about what frequency should we do the adaptive meshing at. Well, now we can do it at multiple frequencies and have a more valid, more accurate solution. And all this can be automated and parallelized with HPC. Another key technology that we recently introduced for ease of use is our new HFSS Auto Solution setup with a new fast mode. The idea behind the Auto Solution setup is, number one, it's easy to use. We're going to require minimal user input. We're automatically going to determine the best mesh frequency strategy The inputs just require the frequency sweep and then a simple 3-point slider bar setting for higher speed balanced or higher accuracy. With the higher speed approach, it's optimized for fast results with good accuracy, and you can use it for early design cycle runs where you want to do rapid iterations. Whereas with higher accuracy, it's a setting for the most reliable results where you do design sign-off. And ultimately, with the slider bar setting and automated mesh strategy, you're trading off between time memory, between speed and accuracy, and really for design runs and sign-off in one design flow. Another new technology I alluded to earlier, and this comes from our SBR Plus solver technology, is real-time radar. Now, what we want out of a real-time radar solution is a range Doppler plot like we're showing here in these two examples of a helicopter over a battlefield and a complex intersection scene for automotive radar example. SBR Plus is a large-scale asymptotic method allowing us to solve these very, very large scenes. And with an Ansys proprietary methodology we call ADP, or Accelerated Doppler Processing, we can take this multi-chirp radar sequence simulation down to one simulation with absolutely no loss in fidelity. It's really amazing, but even this complex simulation scene with standard SBR Plus could take over 10 hours. Now, with the addition of ADP plus some additional algorithmic boost, we can get that simulation down to a minute, but that's still not good enough for real-time radar. That's still not good enough for duplicating what can be done on the test track, where you can take up to 30 frames or more a second. Well, by now deploying this technology on the GPU, we can get this scene generation down to 10 to 20 milliseconds. So now we can achieve more than 30 frames per second. Now we can be quote unquote real time. And this overall hardware acceleration has taken us up to 3 million speed up with this composite acceleration. And look for this real-time radar solution technology in HFSS very soon. Now, another sort of hidden in our presentation is this advanced technology associated with 3D component arrays. And this is this idea of FEM mesh assembly. Remember, in this example here, we have multiple unit cells representing antenna elements and radome corners and radome sides. Well, we take each individual cell and solve it separately, mesh it separately. And then once we have all the cells meshed, we virtually repeat two identical cells, assemble one very, very large mesh, and solve a fully coupled EM system matrix with the domain decomposition method. But one breakthrough here is this technique only requires edge conformal mesh from cell to cell, and it results in no loss in accuracy. That's a big breakthrough. We're no longer requiring conformal mesh everywhere. And if you want to learn more about this technology, take a look at the presentation tomorrow from Hawal Rashid on phased array antenna analysis at HFSS, and then in the SimCom section of our presentation, Keizong Zhao, who will talk about multi-scale electromagnetic modeling for antenna applications, to get more information on this. But one question I want to pose to you, this idea of being able to mesh parts of a model in parallel and only have edge conformal mesh requirement with no loss in accuracy. What if this technology could be applied in general? And what if it was not limited to arrays? So just imagine what we can do with parallelized or concurrent meshing and really lessen the burden of meshing with HFSS. So think about what's coming next with HFSS. And HFSS and HPC, there's been over 2 decades of innovation, starting in 1999 with multiprocessing at version 7, all the way up to our upcoming release 2020 R2, where we made some improvements for our distributed memory matrix solver, as well as for that 3D component array technology, allowing you to use the direct matrix solve option instead of being restricted to DDM. Very broad set of technologies introduced year over year, keeping track with available hardware. Some key ones back in 2014, distributed matrix solver was first introduced. Other interesting ones back in 2008, the domain decomposition method introduced. Ansys and HFSS has been tracking with our customer needs for faster and larger simulations year over year, and sometimes multiple times per year, because it's a constant demand from our customers to solve faster and bigger with HFSS. And the technologies we've discussed today for faster and larger simulations are matrix multiprocessing, distributed memory matrix multiprocessing, DMM, the spectral decomposition method, solving frequency points in parallel, the domain decomposition method, breaking up a mesh and solving them in parallel, doing parallel design points, and hierarchical HPC, all while never compromising the true gold standard accuracy and reliability of Ansys HFSS, because it's only one HFSS. So thank you for attending this presentation, and please take time to attend some of the follow-up presentations over the next 2 days. Thank you.